I'm going to talk about predicting products of double replacement reactions. So first, let's talk about what a double replacement reaction is. In a double replacement reaction, we're starting with two different compounds. Those compounds are going to split up into their component ions in solution, and then they're going to swap ion partners, forming two new compounds. So this must involve substances that can break up into ions in solution. That would include ionic compounds and acids. So those are possible reactants. And then they swap partners, forming new ionic compounds or even acids. So we can write this in kind of a generic form, and I'm going to write it as AB plus CD. So those are my reactants, and I would form new compounds, and what I would form is AD and CB. Now where I got that is, like I said, these break up into cations and anions. So what we have is AB is going to break up into its cation and anion, and so that would be something like A plus and B minus. Okay, now they could have different charges, and you may have more than one of the cation, more than one of the anion split off depending on what the actual compound is, but that's the basic idea. And then CD would do the same. It would split up into C plus and D minus. But again, that could have different charges. You could have multiple of each of those. And those would be all of our ions in solution at the start. And then what's going to happen is those are going to interchange partners. So initially A plus is with B minus. So now that cation A plus goes with the anion D minus, forming AD. And then the remaining cation, the C plus, is going to combine with the remaining anion, the B minus, forming CB. Now one thing you should notice here is the cation's always written first. So the thing with the positive charge is always written first. Another thing that will be more obvious when we look at some examples is that they swap partners and they're going to pair up in a ratio that the charges cancel one another out, where you form a neutral substance. So if these are a +1 and -1 charge, all of them, then they only need to combine in a 1-to-1 ratio. Whereas if you had, say, a +1 charge and a -2, you'd need to combine it in a 2-to-1 ratio. For the first example, we're going to look at the reaction between sodium chloride and silver nitrate. So first what we need to do is we need to break these up into their component ions. So sodium chloride is made up of sodium ions and chloride ions. And silver nitrate is made up of silver ions and nitrate ions. And so now that we have our component ions, what we need to do to predict products is swap partners. So I'm going to take the cation from the first compound, and I'm going to combine it with the anion of the second compound. And we do that in a ratio that makes a neutral compound. So I have a +1 and a -1. You need one of each of those to make it neutral. So the formula of that compound would be NaNO3. And I drop the charges because they cancel each other out, and so you don't keep those. I also write the cation part first. So that's my first product. Then my second one would be the remaining cation with the remaining anion. So I'm going to combine those, again, in a ratio that makes it neutral. We again have a +1 and a -1, so I only need one of each to make it neutral. And so I put those together as AgCl. Again, I drop those charges because they cancel. Also, I write Ag first because that is the cation component. Now we have one last thing to do, and that's to add phases. So you notice our starting substances, we were given that those are aqueous. That communicates that those ionic compounds are soluble. So to figure out the phases of these products that we predicted, we need to know if these are soluble or insoluble ionic compounds. To do that, you look at solubility rules. And you can get solubility rules from your textbook. There's also lots of tables out there. But you should use the one from your textbook. And what you'll see in the solubility rules is something about sodium ion, or group 1 metals. When they're in ionic compounds, those ionic compounds are always soluble. You can also look and see that compounds that contain the nitrate ion are always soluble. So both of those rules are telling you that sodium nitrate is soluble. You actually only need one of those to know that it is soluble. But it tells you it's a soluble ionic compound. So we write that as aqueous, because since it's soluble, it dissolves in water and becomes aqueous. Whereas if you look further at the solubility rules, you'll see that ionic compounds containing chloride ion are typically soluble, but there are some exceptions. So you need to be careful, because when chloride is with silver ion, it's actually insoluble. And so this is one of the exceptions. And since that is insoluble, we would write the phase as solid, because that's something that does not dissolve. So once that forms, it actually sticks together and forms a precipitate. And so this reaction between sodium chloride and silver nitrate is a precipitation reaction. And the overall balanced chemical equation for that reaction would be NaCl, aqueous, plus AgNO3, aqueous, forming NaNO3 aqueous plus AgCl solid. The next example we're going to look at is the reaction between barium chloride and sodium sulfate. So again, we'll start with breaking them up into ions. So the barium chloride breaks up into Ba2 plus and Cl minus, and the sodium sulfate breaks up into Na plus and SO4 2 minus. So now, one thing you might notice here is I didn't take into account how many of each ion are in those compounds. So the BaCl2, that subscript 2 with the chlorine, tells us that there's 2 chlorides for every 1 barium ion, and that's to balance the charges. And then same with the subscript of 2 with the sodium sulfate. That's telling us that there's 2 of the Na pluses for every 1 SO4 2 minus, and that's to balance the charges. So those subscripts are only specific to those compounds to balance the charge. It doesn't necessarily mean that we'll have those subscripts in the products. Whereas the subscript of 4 with the sulfate, that's part of the identity of that ion, so that one stays there. Okay, so now looking at the cations and anions that we have, let's swap partners. So we're going to take the Ba2 plus and combine it with the SO4 2 minus. And so that we have a plus 2 and a minus 2, so those need to combine in a 1-to-1 ratio. So we have BaSO4 is our formula, because we only need one of each of those. And then our second one, we're going to take the Na plus and combine it with the Cl minus, and you have a plus 1 and a minus 1, so you only need one of each of those ions, so that gives us NaCl as our other product. So notice, even though we started with a 2 subscript with the Na and a 2 with the Cl, we don't have subscripts for those in the product, and that's because we only need one of each. You don't need 2 of each to balance the charge. However, we do still need to balance the reaction, and so we have right now 2 chlorines and 2 sodiums on the reactant side, but we only have one of each on the product side. So that's where we'll put a coefficient of 2 in front of that NaCl. So we form 2 moles of NaCl for that reaction. Whereas the barium sulfate, you start with one barium, you end with one barium, and you start with one sulfate and you end with one sulfate. So we don't need a stoichiometric coefficient there, nor do we need any in the reactants. So those are our products, but then we still need to consider the phase of each product, and in that case, since these are ionic compounds, you use solubility rules. And so in the solubility rules, you should see information about sulfate ion, and that ionic compounds containing sulfate are typically soluble. However, there are some exceptions, and if you look at those exceptions, barium is an exception to that, meaning barium sulfate is an insoluble ionic compound, so we would write that as a solid. And then, if we look at our sodium chloride, you can either look in the solubility rules and see that compounds containing sodium ion are always soluble, or you look at compounds containing chloride ion are generally soluble, with sodium not being an exception. So that means sodium chloride is a soluble ionic compound, so we write that as aqueous. So, from this reaction, you'll see we do form a solid, our barium sulfate, so this is a precipitation reaction. And if you want to write out the entire balanced chemical equation, you're going to have BaCl2 aqueous plus Na2SO4 aqueous forming BaSO4 solid plus 2NaCl aqueous. And that would be your overall balanced chemical equation. Next, let's look at the reaction between cobalt-2 chloride and sodium carbonate. So we'll break these up into their ions. We have CO2 plus and Cl minus, and then Na plus and CO3 2 minus. Again, I don't care that there's 2 chlorides and 2 sodiums in an individual unit of each of those compounds. All I need to know is what is the cation, what is the anion in each, so that I can swap partners. Now we can swap our partners. We take the CO2 plus and the CO3 2 minus and combine those, and we get CO, CO3, because I have a 2 plus and a 2 minus, so I only need one of each of those to make a neutral compound. And then I combine the Na plus with the Cl minus. I have a plus 1 and a minus 1, so I have NaCl. So out of those now, we can think about phases. And if you look in the solubility rules, you'll see that CO3 2 minus, or carbonate ion, when that is an ionic compound, it's typically insoluble, and when it's with cobalt, that is not an exception. So our cobalt-2 carbonate is an insoluble compound. And then sodium chloride, which we already looked at last time. Remember, sodium and chloride, both of those things are soluble, or sodium ion is always, chloride is most often and always with sodium. And so that is a soluble compound, so it would be written as aqueous. And then one other thing we need to consider, we've got our products, we've got our phases, we also need to consider balancing. So the starting substances, we had 1 cobalt, ending we have 1 cobalt, starting we have 1 carbonate, ending we have 1 carbonate, and then starting we have 2 sodiums, and so ending we need 2 sodiums, and starting we had 2 chlorines, and now we have 2 chlorines in the end. And so if we put all of that together to get our overall chemical reaction, our overall balanced chemical equation, then we would have COCl2 aqueous plus Na2CO3 aqueous forming COCO3 solid plus 2 NaCl aqueous. Okay, next up, let's look at copper 2 sulfate reacting with sodium chloride. So we break these into ions. We get Cu2 plus and SO42 minus, and Na plus and Cl minus. So we can take those ions and swap partners. Put the Cu2 plus with the Cl minus. And so we need to balance charges when we combine those. So we have a 2 plus and a 1 minus. We're going to need 2 of those 1 minuses to make it neutral. So our formula is CuCl2. And then the next one, we're going to take Na plus, combine it with SO42 minus. And so we're going to need 2 of the pluses to balance out the 2 minus. So our formula is going to be Na2 SO4 to make a neutral compound. Now let's think about balancing. We started with 1 copper, we end with 1 copper, but here we start with 1 chlorine and end with 2. So we're going to need to put, whenever we write our full reaction, we need to put a 2 in front of that NaCl. And then we start with 2 sodiums now. We end with 2 sodiums. And we start with a sulfate and end with 1 sulfate. So that would be balanced. Now let's think about phases. So if we look at solubility rules, you'll see that chlorides are generally soluble, and copper is not an exception to that. So that means the copper 2 chloride is a soluble substance, so it's aqueous. And then our next one, we've got sodium sulfate, and sodium is always soluble. So we don't really need to look at sulfate, but if you looked at information about sulfate, you'll see it's generally soluble, and sodium is not an exception. So sodium sulfate is also soluble, so aqueous. Now, we could write the overall reaction, the copper 2 sulfate plus the 2 sodium chlorides going to copper 2 chloride and sodium sulfate, but in reality, there's actually no reaction occurring, and that's because we're starting with aqueous substances and we're ending with aqueous substances, okay, or at least aqueous ionic compounds. And when an ionic compound is written as aqueous, it doesn't actually exist as this neutral substance that we're writing. It exists as just ions. And so you just have a bunch of Cu2 plus, SO42 minus, Na plus, and Cl minus to start with. And then in the end, we also just have those same ions. So actually nothing's really happening. And so we usually wouldn't even write that overall reaction. We would instead just say that it is no reaction, because in reality, we didn't form a precipitate here. We didn't form a precipitate, and we didn't form anything else that would kind of pull out of solution, okay? Nothing that would separate itself in some way. The only other things in addition to precipitates, so solid ionic compounds that we could form that would cause a reaction, would be if we formed water, then that actually forms, or some sort of gas, then that would cause an actual reaction. But in this case, if you're starting with ionic compounds that are soluble, so aqueous, and you're ending with ionic compounds that are soluble, or aqueous, then there's actually no reaction. Okay, next we're going to look at a reaction between hydrobromic acid and calcium hydroxide. So this is actually an acid-base reaction because we have an acid reacting with a base instead of what we've been looking at, which are ionic compounds reacting, doing precipitation reactions. But to predict the products of an acid-base neutralization, we go through the same steps. So I'm still going to break these up into their cations and anions. So HBr would split up into H plus and Br minus when it's in solution, and the calcium hydroxide would break up into Ca2 plus and OH minus. Again, just like with the ionic compounds, I'm ignoring that subscript of 2 with the OH because that's simply there to balance the charges for the Ca2 plus and the OH minus. We don't necessarily need that in the product. So I just want to focus on the ions. Now that we have our cations and anions, we're going to swap partners. So the H plus goes with the OH minus. And those, when they combine, you might initially want to write it as HOH because that's your cation, then your anion, but it's more commonly written as H2O. Okay, so we form H2O by the combination of H plus and OH minus, and then our remaining cation, our Ca2 plus and our Br minus, combine, and that forms then CaBr2, because I'm going to need 2 of those negative ones to balance out our Ca2 plus. So those are our products, and that means we would have to do some balancing. So the Br, I need 2 of those, so I'd put a 2 in front of the HBr, and then that's going to cause 2 waters to be formed because I have 2 H pluses that are going to be coming off of this and 2 OH minuses from the reactants. And so I actually form 2 waters. And so that would be our products and our balancing, but then we have to determine our phases. Now, for ionic compounds, you use solubility rules. So out of these 2 products, the calcium bromide is an ionic compound, and so we would need to consider that bromides, just like chlorides, are typically soluble, and calcium bromide's not an exception. So that would be a soluble ionic compound, so we would write that as aqueous. Okay, but then we have water, H2O. That, unless if we were under some odd conditions, so if we were at a higher temperature or really cold temperature, then water is just going to be a liquid. And in the case of, acid-base reactions or anything like that, it's typically in the liquid phase. It would only be in the gas phase, say in like a combustion reaction where lots of heat is produced, or if for some reason we were cooling this down, you could solidify it. But in this case, it is a liquid. Okay, so we have our balancing, we have our products, we have our phases, so we can put all of this together and get our overall reaction, which would be 2HBr aqueous plus CaOH2 aqueous, forming 2H2O liquid plus CaBr2 aqueous. Okay, for our final example, we'll look at the reaction between hydrochloric acid and sodium hydrogen carbonate, or sodium bicarbonate. So this is also going to be a double replacement reaction, or at least to start with. So we're going to predict the products just like before. We'll break these up into ions. We have H plus and Cl minus, and then Na plus and HCO3 minus. So those are our cations and anions, and we're going to swap partners just like before. So the H plus is going to go with the HCO3 minus, and so what that's going to form is H2CO3, which is actually carbonic acid. And since that's an acid, it actually has a phase of aqueous. And then we're going to form NaCl from our Na plus and our Cl minus. And we've seen before that that's a soluble salt, so that one is aqueous. Okay, so those are our products, or at least our initial products that are formed from the double replacement. However, in some instances, what's initially formed by that double replacement is some substance that then further breaks down. The most common of these, the ones that you would actually run into, are when you form carbonic acid. So carbonic acid isn't going to be stable. It's much more stable if it breaks down into more stable compounds, which what it breaks down into are water and CO2. So this carbonic acid is actually going to further react very quickly actually and form H2O and CO2. And so the H2O is a liquid and CO2 is a gas. So the H2CO3 or the carbonic acid is kind of an intermediate product. And so sometimes people write down that as the product, but it doesn't stay in solution for very long. It pretty quickly breaks down into water and CO2 because those are much more stable compounds. And so that's where you would see when you combine these things, you'll see bubbling occur. And that bubbling is the CO2 gas coming out of that solution. So for this reaction, the overall reaction would actually be HCl aqueous plus NaHCO3 aqueous forming H2O liquid plus CO2 gas plus NaCl aqueous.